we need to look at exponential growth. Now replacing the original function by a model. So instead of using an expression that tells us how the growth goes over time, we want to actually simulate the variable, namely the thing that changes, in an update rule. So how would we do that? Then we have an update rule specified here. It's the simple thing of a doubling of a population over the course of time, where we have an expression that tells us on the left-hand side nj, we have a population represented by the numbers of individuals that are in it. Nj is the number, and j would represent the time point at which you want to have it calculated. How do you calculate it? Well, the equal sign shows you on the right-hand side an expression. The mathematical expression is you take the previous population, go one step back in time, and check what was the population at that time, multiply it by 2, and this is how you get the current population. And as you can do that for any time point, this label j and j minus 1, of course, can take any natural number as long as it's positive. A specific feature of this very simple population is the number 2. 2 meaning that we have an instruction that the population of the previous time point is taken times 2 to produce the new population, means it doubles the population in the period that we're going to look at. Now, if that is something that is flexible, can, for example, change from one bacterial population to another bacterial population, then we would refer to that specific time as the doubling time. And it can be said 20 minutes for one type of bacteria, it can be 30 or another time for another type of bacteria. So we have expressed the growth of the population or the change of the population in steps of the doubling time. So each time we advance by the doubling time. This is specific. It means we don't advance in steps of unit time. So we are going to now try to base, if I just place this with my Matlab window, open a new script file, and we now would like to have a piece of code that implements this model of a discrete update rule, not a function, a discrete update rule, in terms of the doubling time. Say, if we just take an arbitrary number, say 20 minutes, so rather than putting it per minute, we say in steps of the doubling time, 20 minutes. So first we create an array, and that should be a comment, of the time steps that we want to calculate. So how do we calculate this? Say the T sub PTS, the time points, can be defined in an array S going from 0 to some final time, and I have it written here, 120. And if you remember, if I take it in this convention, this will make an array that advances in steps of 1. If we want it in steps of the doubling time, we can put the doubling time within semicolons, within the colons, and would get an array from 0 to 120 in steps of 20. If we execute it and take a look at what this looks like, then we see it turns out that we have 7 entries. We have 7 numbers starting from 0, ending at 120, and indeed the numbers we seek advance in steps of 20. Take that away. So this is our basis. These are the time points where we want to have the model calculated. And what we can do here is we can now define our array that takes the population. So our results will be collected in a result vector, and that result vector will be defined as n, say the number, and the number is given by zeros. We just initialize it with zeros. We have one row, take this away, and we'll have a number of steps. In this case, maybe 7 steps. Would have 7 steps for one to calculate it. Now we had that before. Often we would like to replace specific numbers by symbols in order to be able to flexibly handle different values for that one thing. So if that is the number of time points that we want to calculate, we need to find out how many time points are there. It's very easy because we can apply the Matlab function length to our array tpts, and if we do that, as you can see, the answer on the right hand side is 7, so the length of that array is 7, and we would then create a result vector that has 7 zeros to start with. Put a semicolon here to suppress the output, and we will use this later on to be more flexible than just the doubling time of 20 minutes in this case, but define another more flexible way of dealing with the times we advance over the simulation. So now, having defined our result vector, we can then start to initialize. Why would we need to initialize? Initialize because we are dealing with a simulation. We can no longer just use an abstract function. We need to say what will be the starting value of that population. So how many individuals will there be to start with for the first time point that we give into our model. So similar to the initial volume that we had defined previously, now we give the initial population value, and it would go in this area, it would go in the first entry, and we can define something, say we're dealing with 100 individuals, so our entry n of 1 would be 100. So that's the number to start the calculation with. And now, to make things happen, we need to do the simulation, the actual simulation. And you're familiar with for loops, would go in a for loop, successively iterate things, starting from that initial population until you get to the last time point. So if we call our running index j, then this index j would start to run from the first one we have defined already, so we would take the next one to start with number 2, and it would go all the way to the end, but n, we know what n is, namely is the value that we have assigned to nt. I haven't really defined it, so I need to do that now. Equal to this. If the length of the array is called nt, then we can refer to this length in the result vector and also in the maximum value, the upper limit of the index. As we know, each for loop needs to be stopped by an end, so that will be the parentheses that contains our code, and the update rule is fairly simple to write. It's a single line. You know it from having, for example, implemented the Fibonacci series. The entry nj, so the population number at the time point represented by j, will be calculated as twice the population number at the time point that was one doubling period before, and that's j minus 1. So the new time point is calculated as 2 points the previous time point. So this is the implementation of the algorithm that we had from our model description in the slide previously. And how can we view the results? Once the calculation is finished, we can just use plot as usual take a look at our result. We would have the time points on the horizontal axis, we would have our array n on the vertical axis, and we can use, for example, stars as symbols to display the actually calculated values, and then say that we want to see them in black. If we try to run the code, we can get the information that there is a wrong parenthesis here, and the reason is that I have stopped this whole process too early, and that the closing parenthesis needs to go only in the end and not be doubled anymore. So another check, run the code means we're getting output in a graph, the graph showing us how the population will evolve from the initial population of 100. If I just put it as we did it before again, we'll have the Y label population, which is the number of the individuals there, and on the horizontal axis time tells us how it advances, and we can see that for every 20 minutes advance in time we get a dot, and we can already get an idea of how this population grows. Namely, it doesn't grow linearly, but it grows, if you look into the materials, in an exponential fashion. So exponential growth means we have a growth that is more than just linear growth, and we can remember that this is of course dependent on the fact that each individual doubles. So if we think of cell division, that the doubling of the individual is what makes having the increase, the increment over the doubling time, getting larger and larger. Because there are more individuals, then by doubling the number, there will be also more individuals created. In a sense, that's all that we need. One question that we might ask here, if you have such a model and you look at the one line highlighted now in yellow that expresses our update rule, how would you change that model in order to describe linear growth? If you're thinking of something that represents our volume from before, from the initial function, we know what a linear function looks like. It's a straight line with a certain slope, and this is not what we get when we have exponential growth, and as in the current case.